Good morning and welcome back to the Johnson Space Center for the continuation of our pre-flight briefings today. We're previewing the STS-117 space shuttle mission, which is also the 13A assembly mission to the International Space Station. For this briefing, our participants will be providing an overview of the mission. To do that, we have the lead space shuttle flight director for the flight, Kathy Kerner. To her right, we have the lead space station flight director for the flight, Kelly Beck. And to her right, we have the lead launch package manager for this flight, Floyd Booker. As usual, we'll open up with comments and then take questions from NASA centers. Kathy?
Good morning. I'd like to start out this morning by introducing you to the Crew of Atlantis. We have a 6-member crew. Half of them are veterans and half are first-time flyers. The crew is led by Commander Rick Sturkow. When you hear us talk to the crew, you'll hear us refer to them sometimes by their call signs. Rick's call sign is CJ. CJ is a colonel in the United States Marine Corps. This will be his 3rd mission. Both of his first 2 missions were to the International Space Station, but this is his first mission as commander. Our pilot is Lee Archambault. Lee's call sign is Brew. Brew is a colonel in the United States Air Force and a fellow graduate with me of the University of Illinois. This is his first spaceflight mission. And in addition to his pilot duties, he is one of our 3 robotic arm operators. He's also prime robotic officer for the space station arm. Pat Forrester is our mission specialist number 1, or MS1 as we refer to him. Pat is a retired colonel in the United States Army. This is Pat's 2nd mission to the International Space Station. On his first mission, STS-105, he performed 2 spacewalks. Pat is one of our spacewalkers for STS-117 and is our prime shuttle robotic arm operator. Steve Swanson is our MS2. His call sign is Swanee. He has a doctorate in computer science and is another one of our spacewalkers. He'll be doing his spacewalk with Pat, and he's also one of our robotics experts. This is his first spaceflight mission as well. Danny Olivas is our mission specialist number 3. Danny has a PhD in mechanical engineering. This is his first spaceflight mission, and he'll be performing 2 of the spacewalks on this flight. And last but certainly not least is Jim Riley. He is our MS4 and he goes by JR. He has a PhD in geosciences and is an officer in the Navy Reserve. He has 2 previous space flights under his belt, one to the Mir and the other to the International Space Station, and has performed 3 spacewalks on his previous missions. He is scheduled to perform 2 spacewalks on this flight. Now I'd like to show you the patch of STS-117. It was designed by the crew. This patch symbolizes the continued construction of the International Space Station and our ongoing human presence in space. The ISS is shown orbiting high above the Earth. The crew will install the portion of the space station that is highlighted here in gold. It consists of the 2nd and 3rd starboard truss sections, or what we refer to as S3, S4, which includes a set of solar arrays. The names of the crew are above and below the orbiting outpost. The 2 gold astronaut office symbols, which are emanating from the bottom 117, at the bottom of the patch, represent the concerted efforts of the shuttle and station programs to complete the International Space Station. The shuttle and unfurled banner of red, white, and blue represent our nation's renewed interest in patriotism and the continued exploration of the universe. I'd now like to introduce you to our Space Shuttle Flight Director team. For launch and entry, Norm Knight will be in control in the Mission Control Center. You may recall Norm from STS-116, where he was the entry flight director. I will be the Orbit 1 flight director, and my shift will start at the beginning of the crew day. Approximately midway through the crew day, I will hand over to Brian Lunny. Brian is our Orbit 2 flight director. He worked with me on STS-115, and he and his team will be on console during the latter part of the crew day. Our planning shift, or Orbit 3 flight director, is Richard Jones. This is Richard's first full mission as a shuttle flight director, although he did work with me also on 115. Richard and his team will be on during the crew's sleep period and will have charge of replanning the crew day should that become necessary. Because this mission is potentially going to be longer than 11 or 12 days, we have a pre-launch planning shift flight director, and that is Mike Moses. Mike is not only going to be working pre-launch, but he may very well substitute in near the end of the mission, depending on how long the mission becomes. As many of you know, the primary objective of STS-117 is the delivery of the S3, S4 segment to the International Space Station. We have, I believe, a graphic that shows the payload bay configuration. What you'll see in the graphic is the orbiter docking system up near the crew cabin. That's very standard. On the port side, you'll see the shuttle remote manipulator system, or SRMS. That, along with the orbiter boom sensor system on the starboard side of the vehicle, that comprises the two arms that we will use for inspection on Flight Day 2 and then late inspection currently planned for Flight Day 10. And of course, the biggest element that we have in the payload bay is the S3, S4 truss, and Kelly and Floyd will both give you much more details about that later on in the presentation. STS-117 is an 11 plus 2 day mission. What that means is we have 11 planned days containing 3 EVAs. The first plus 2 means that we have 2 additional days of consumables, which would allow us to extend the mission for primary mission objectives. The last plus 2 is the 2 days that we have for standard end of mission wave-offs, either for weather or for orbiter anomalies. Between Kelly and I, we will walk you through the mission day by day. See, Flight Day launch is currently, Flight Day 1 is our launch day. Its launch is currently scheduled for 6:43 a.m. Eastern Time on March 15th. Launch day will look very similar to previous missions in that post-launch, the crew will configure Atlantis to support on-orbit operations. This includes setting up our computer network and powering up and checking out the robotic arm. Flight Day 2 has, since return to flight, become our standard inspection day. Both Brew, Pat, and Steve will take turns inspecting Atlantis' thermal protection system. Since return to flight, we've essentially done the same set of scans. I think we have a video that shows what those scans look like on Flight Day 2. This mission, we've incorporated some of the lessons learned from previous flights. Since return to flight, these scans have been pretty much the same. In this flight, they're going to be a little bit different in that we've made them more efficient. We've automated some of the maneuvers. Probably the most recognizable change for those of you who are studying our flight plan is that we no longer have a separate procedure for the crew cabin survey. Instead, the crew cabin survey is integrated into these scans. If you watch the video, you'll see that the sides of the crew cabin are being illuminated when they're on the starboard and the port wing. We perform the starboard wing scan first, followed by the nose cap, and then the port wing scan. While the scans are going on, JR and Danny will be checking out their suits for the spacewalk that will take place on Flight Day 4. See, the inspections take pretty much the full Flight Day 2. Flight Day 3 then is our standard rendezvous day. The crew will wake up and pretty quickly begin performing a series of burns, which will bring us from behind and below the International Space Station. As we've done since return to flight, we will pause at about 600 feet below the station and perform an RPM, or R-bar pitch maneuver, sometimes also referred to as the rendezvous pitch maneuver. This maneuver allows the crew of the International Space Station the opportunity to photograph the orbiter, most notably the underside. And the current crew on board the International Space Station is experienced taking these photos. They took these photos for STS-116, and our plan is to have them on the ground actually before docking so that our imagery experts can verify the integrity of the thermal protection system. After the RPM, we will maneuver to the V-bar in front of the ISS, and pretty much from here on in, it's a very standard docking, as we have done many times before. After hard mate and leak checks are complete, we'll open hatches, conduct a meet and greet, and a safety briefing, which is again very standard for ISS missions. And then we'll get right away to work removing the S3, S4 payload from the payload bay and handing it off to the station arm. Pat will be removing the element from the bay and handing it off to Brew, who will be operating the station robotic arm. And at this point, I'm going to hand off to Kelly.
Thanks, Kathy. Well, good morning, everybody. It's really good to be here finally to talk about 13A. There's been a lot of folks that have worked many years getting ready for the mission and getting us to this part in our timeline. So we're glad to be here, and I'm really glad that we can sit here and tell you about our plan and answer any questions you might have once we're done. I'm sure you're all familiar with the Expedition 14 crew since they are on orbit, but I thought I would reintroduce them just to remind everybody who will be there during the 13A mission. The ISS commander, Michael Lopez Alegria, and the flight engineer, Mikhail Turin, have been on board since their launch on Soyuz back in September. And you see we call Mike LA, so you'll hear me refer to him as LA. He's in the center of the photograph. And then Mikhail Turin is on the right-hand side of the photograph. Flight engineer Sunny Williams joined them in December. She arrived on the 116-12A.1 mission. The station crew will be supporting, along with the shuttle crew, to do the various activities during the 13A mission. We also have an image of the Expedition 14 patch, and this was designed by the crew. The 5 stars that you see on the patch honor the U.S. and Russian missions in which space travelers had lost their lives. The Roman numerals for the number 14 are in the form of an ancient Spanish chariot, and that's to honor LA's home country. And it's depicted orbiting around the moon and to Mars to symbolize exploration. So that's what the patch looks like for Expedition 14. Next, I'd like to introduce the station flight directors who, along with myself, will be providing around-the-clock support during the 13A mission. We have Annette Hasbrook, is the ISS Orbit 1 flight director. She'll be on console when the crew wakes up, and she'll be with them through the first part of their morning. Then I'll be on the Orbit 2 shift on console during a majority of the crew's day. Then we'll have Holly Ridings, is the Orbit 3 station flight director, and she'll be with the crew when it's time to say goodnight, and also through their sleep period, putting the plans together for the following day. Floyd's going to be talking to you in more detail about the S3, S4 segment, but I just want to give you a little bit of an overview so that you can kind of put things in perspective as we start talking about the mission activities day by day. As Kathy mentioned, our primary objective is to install the S3, S4 truss. That's going to provide the station with a 3rd set of solar arrays and the associated electrical, thermal, and command and data handling components. I'll start kind of working right to left. The S3 segment is in the right side of the picture. It includes the segment-to-segment attach system, which is the system that we'll use to permanently attach this element onto the starboard side of the truss. It also contains a mobile transporter worksite that we designate as Worksite 1, and that will be used during the 13A.1 mission to install the next piece of the truss on the starboard side called the S5 segment. The S3 element also contains 4 payload attach systems that will eventually house external payloads. The S3 and S4 segments are joined by what's called a solar alpha rotary joint, and you'll hear me call this SARJ. That allows the solar arrays on the S4 side of the element to track the sun from sunrise to sunset. Working our way to the left, the S4 segment actually includes the 2 new arrays and the electrical components that will distribute the power from those arrays. And we designate the arrays and the associated power channels as 1A and 3A. So you'll hear us refer to those power channels with that nomenclature. Each power channel is going to give us about 14 kilowatts of additional power generation, so we're taking a major step in our power generation capability with this element. We also have the Photovoltaic Radiator. That is the piece of equipment that provides cooling, ejects the extra heat generated by the electrical components associated with the power channels. So that's the high-level overview of what the 13A mission will be delivering. Now I'll pick up where Kathy left off on Flight Day 3. She left off where the station arm had the truss in its grasp, and it will remain there overnight. The rest of the Flight Day 3 activities are really getting ready for the EVA the next day. At the end of Flight Day 3, JR and Danny will get into the airlock. They will reduce the pressure in the airlock and also breathe pure oxygen. This is part of one of our protocols that we use to remove nitrogen from the bloodstream, and that's just a standard protocol that we need to use to make sure that we don't have any issues with decompression sickness, otherwise known as the bend. So this is a standard protocol that we've been using since the 12A mission. We'll be using it during the 13A mission. Flight Day 4 is really the big day where station is going to take on a new look. We have an image, sort of the before shot, if you will, what the station looks like today. We have the, on the upper right quadrant of the picture, you see the P3, P4 segment with those solar arrays on the port side of the vehicle. The lower left quadrant is where we'll be installing the S3, S4 truss, so it'll start to look asymmetrical again once we complete our activities. And then you see the 2B array that sits up on top station that is currently deployed, and that is one of our objectives, to retract that solar array. So when the crew wakes up on flight day 4, they're going to begin their robotics and EVA preparation activities. The airlock will be repressurized. That'll allow JR and Danny to get out, do their morning routine, grab some breakfast, go back inside, and then they'll be assisted by LA and Steve Swanson to get them suited up. In the meantime, while they're getting ready for their spacewalk, Brew and Sunny will be performing the robotic operations to install the truss, and we can pick up the animation where Kathy left off. Brew and Sunny will be taking the space station arm through a series of maneuvers to position the truss into the proper orientation for installation. Once they have that in the proper orientation, then Sunny and Pat Forrester will operate the segment-to-segment attach system to permanently attach that module. The first step of that is operating a claw-like mechanism on the S1 side of the interface, and that claw will close around a capture bar on S3, bring the two segments together tightly so that then they can start the bolting sequence. And then Sunny and Pat will do the bolting. Once that's complete, Brew and Sunny can ungrapple the station arm and maneuver it into a position to watch the EVA. By the time the truss is securely attached, the spacewalking crew will be ready and suited up. Keith Johnson later today is going to give you more details on the EVA, but again, I just want to give you a high level so you know how it fits into the general mission plan. First thing that they'll be doing is they will mate the umbilical connections to provide power and command to the components on the truss and also receive data from those components. The next thing they'll be doing is preparing the solar arrays for deploy, and we have an animation of what that will look like. They'll first release the restraints so that the mast canisters, the circular cylindrical canisters that house the mast, the central structural member, they'll deploy those into position, and then they'll release the restraints on the boxes containing the solar array blankets, and they'll swing those out into position in preparation for deploy the following day. The crew will also release the restraints on the radiator so that it can be deployed later on in the EVA. They will start the preparation tasks for the solar alpha rotary joint. They'll be repositioning 4 struts that provide additional structural integrity to take the on-orbit loads. They'll also be positioning one of the drive lock assemblies. This is the mechanism that rotates the joint and also locks the joint when it becomes operational. And they'll start to remove the launch lock. So they'll get a good head start getting the Sarge prepped for its operational state. While the crew is out performing their spacewalk, the ground will be activating the new systems and getting the power channels up and ready to support loads. Towards the end of the spacewalk, the crew inside the vehicle will command the radiator to deploy, and we have an animation of that as well. The deploy of the radiator is much more straightforward than the solar arrays, which I'll talk about a little later. It'll take about 10 minutes for the radiator to fully deploy. Once that's complete, the ground will be continuing overnight with the activities to prepare for the solar array deploy the next day on flight day 5. Before the crew wakes up on flight day 5, the ground will have unlatched those boxes containing the solar array blankets, and they'll have deployed the array's 1 mast bay. And you'll hear us refer to that nomenclature a lot, a mast bay. That central structural member between the blankets we refer to as the mast. And you'll notice that it's divided up into segments, and we call each of those segments a bay. So you'll hear a lot of that discussion when you hear us talking on the loops. So that'll get the arrays in a good configuration with just being deployed a short amount, just that 1 bay amount, so that the crew can take over when they wake up. We will be using the same technique to deploy the solar arrays as was used on the 12A mission to deploy the P3, P4 arrays. We had some lessons learned from STS-117, the 4A mission. That was the first time we had deployed a U.S. solar array on station, and that was the 2B array. And we had continued to do the deployment and saw really a lot of dynamic motion in that, and we're trying to use this new technique to avoid that. And we do have a video clip I can kind of show you a compare and contrast to what we did on 4A. If you focus your attention down towards the base of the array, what happened is these panels tend to stick together, and then as the mast was being deployed, the panels would release, and they would do that fairly dynamically, and you can see how there's a wave that propagates up and down the array, and those panels towards the base moved quickly into the blanket box, and that did cause us some problems with the tensioning mechanism that the crew had to go outside during a spacewalk and correct. So the new technique is designed to avoid that dynamic motion. And basically what we do is we deploy the array about halfway out. We let it sit with sun shining on the panels so that those panels can warm up. And as they warm up, they tend to release. And so we'll sit there for 30 minutes and let the panels release. And this is video of the 12A mission. And you see that although there's motion with the panels releasing, you don't see that wave up and down the array. So that's what we hope to accomplish with the 1A and 3A solar array deploys on our mission as well. We do have an animation of our deploy sequence. And again, this is with a lot of our animations, it's a little bit faster than we'll be doing in reality. We'll deploy the 1A array first to the halfway point, wait for 30 minutes with sun on it, and then complete the deploy of that array. It will be repositioned, and we'll do a small attitude maneuver to get sun directly on the 3A array. It will be deployed halfway, same sequence, wait for 30 minutes to warm the panels, and then complete the deploy. Let's see, the next thing I'd like to talk about is at the end of this day, the mobile transporter will be translated to worksite 3, and that's going to be in preparation for the next day's activity. And we have animations so that you can see where those work sites are located. Again, much faster than real time, but we move from worksite 2, where the station arm and the mobile transporter was based for the installation and to watch the solar array deploy. It then moves to worksite 3 so that we can be in a position to watch and support the 2B retract. Since the next day is the second spacewalk, we do have 2 EVA teams, as Kathy described. So the second set of spacewalkers will be going out the door the next day. So Pat and Steve Swanson will be getting into the airlock and repeating the same protocol, camping out in the airlock overnight, just as JR and Danny did before their spacewalk. Flight day 6 will be our second spacewalk, and we'll also be starting the retraction of the 2B solar array. The opposite P6 array, the 4B array, during the 116 12A.1 mission, we did experience some problems with that retraction, and so we're going to develop our plans to try to account for some of those lessons learned when we go about retracting the 2B array. I do have some pictures from the 4B array retract just to help describe the problems that we experienced. The first thing they experienced was the panels not wanting to fold properly. And during the 12A mission, they used a pretty good analogy of folding a map. If you've ever tried to fold a map, if you don't have the creases just lined up quite right, it's very difficult to get it to fold up properly. So it's a similar case here. You'll notice the vertical lines are the hinges. And those hinges had some bows in them so that the arrays did not want to fold up properly. So that is one problem that we're anticipating with the 2B array. I also have another picture showing a second problem that was encountered with the guide wires hanging up. And you can kind of think of the solar array sort of like window blinds, that these guide wires run through the center and through the edges of the array, and that's to tend the solar array panels so that they neatly, just as if you were raising a blind, how the panels and the blind would stack up. And so what happened is these guide wires were getting hung up on the small rings that are attached to the arrays that the guide wires go through, and it was causing the panels to be retracted unevenly, and they were getting hung up. So what we're trying to avoid is that stack of panels being brought down towards the blanket box and then possibly spilling out of the blanket box. So as I said, we're expecting that we're going to have similar problems with 2B, so our plan involves the initial retraction before we ever send the crew out of the airlock for their spacewalk. We hope to have about an hour of time to try to get the array to start the initial retraction and see if we're going to have that same backward panel folding problem that the 4B array experienced. If we do have that problem, we'll have some time that we can try to redeploy the array and then start the retraction again to see if we can correct the problem that way. If not, then the whole reason for doing it before that second spacewalk is that gives us the opportunity to have Pat and Steve correct that backward panel folding during their EVA. So once they head out the door, we'll get Pat on the station arm, and Steve will also be up on the truss on the other side so that they can both assist us to get retracted. We're shooting for 2 or 3 mass bays because we think if we can get it retracted that far, we'll have a good clear indication that the panels are folding properly. So if we need them to, we'll have them go up and push on that hinge so that the panels are allowed to fold up properly. Once we are done with the 2B, that small amount of 2B retraction that we're going to be doing during that second spacewalk, then Pat and Steve will continue on to their other tasks, which involve prepping that solar alpha rotary joint. They will be positioning the second drive lock assembly so that the ground can engage that. They'll be installing brace beams, which provide additional structural integrity for the element to carry on-orbit loads. And then they'll also start to release the launch locks. We hope that if we can finish up with the 2B early on and get it into a configuration that we can then pick up with deploy from the inside of the station on the next day, that we'll be able to get this SARG prepared and ready for operational use once we do get the 2B array retracted. So on flight day 7, if things have went well on that second spacewalk and we have 2B in a configuration where we can continue the retraction, the crew will be doing that from inside, sending the commands from inside the vehicle, retracting 1 bay at a time, and then we've also are going to be incorporating sinusoidal motion of that beta gimbal assembly to try to keep those guide wires from hanging up on the grommets. And we have an animation. We'll retract the 1 bay, and then command motion in one direction for about 5 seconds, reverse direction, and then repeat that sequence 8 to 10 times. It really depends on how far the array is out, with the goal of trying to keep those guide wires from hanging up. Once we get the 2B array retracted as far as we're able to, then the crew will have some off-duty time. That's to give them some time to rest up from the busy mission that they've had so far. We also have an alternate plan for flight day 7. As Kathy mentioned, they'll be doing planned inspections of the orbiter thermal protection system. And by this point, the teams on the ground will have time to look at that data and determine if there's any areas that we need to take a closer look at. If we decide that we do have areas that we need to do what we call a focused inspection or take a closer look, then instead of doing the 2B retract, we will put those focused inspections in the plan. And we have an animation here. Because of the clearance and the reach of the shuttle arm, the station arm actually has to unberth the boom. So it will reach into the payload bay, unberth the boom, rotate it into a position so that the shuttle arm can accept it, and then the shuttle arm will grapple and then perform the inspection. So that's our alternate plan for flight day 7. At the end of flight day 7, JR and Danny will be doing the spacewalk the following day, so they'll get back into the airlock, camp out overnight, just as they did before their first spacewalk. Flight day 8 is the last of the nominally planned spacewalks. JR and Danny will be assisting the crew on board to get 2B fully retracted. It'll really depend on how successful we've been on flight day 7 as to how long it's going to take us to get that array retracted during this third spacewalk. We are expecting that JR and Danny are going to have to free some hung guide wires, and we do have some video just to show you what that might look like from 12A.1. Here, Robert Kerbeam was using a tool just to kind of move those solar panels past the part that was getting hung up. And so we do think we'll have to do similar operations on this third spacewalk. If there's time left in that spacewalk after we get the 2B array retracted, JR and Danny will be performing tasks necessary to clear the path out to the new work site 1. And they will also, if they have enough time, they'll be replacing a vent. It's currently a water vent that allows us to vent water through the lab. They'll be replacing that with a hydrogen vent, and that is to support the new oxygen generation system that will be brought online sometime after the 13A mission. Basically what this system does is it takes water and produces oxygen, and then as a waste product it will produce hydrogen, which will be vented overboard. Once the 2B retract is completed, then the station is going to take on that new look that I had described. We have the after shot now that shows now that vacant spot on the starboard side of the truss is occupied by S3, S4 and its solar arrays. And then you'll notice at the top of the picture, there is no longer the 2B array deployed. It will be fully retracted. That will allow the SARGE to rotate on the starboard side, and we have an animation that shows what that will look like. You'll see now that both the arrays on the port and starboard side of the vehicle will be free to rotate and track from sunrise to sunset. So it will look significantly different. Assuming we've had enough time to clear the translation path during that third spacewalk, at the end of this day, we'll be moving the mobile transporter to Worksite 5. We have another animation here. We'll take it to Worksite 5 in preparation for the following day's activities to walk the arm off to the lab. So on flight day 9, Mike and Sunny will be walking the station arm from the MT onto the lab, and that's just so the first time we go to a brand new work site, we don't have the arm on the mobile transporter. It's not required, it's just we have time in the timeline to do it that way, so that's the plan. Then the MT will be translated out to work site 1, the ground will perform the checkout, and then it will be translated back to work site 4, where it will remain until closer to the 13A.1 mission. On this day, flight day 9, the shuttle crew also has some additional off-duty time. That's to let them rest up for entry. They will then later in the day be performing their final goodbyes, final transfers, and at the end of the day, they'll close the hatches in preparation for undock the next morning. And at this point, I'd like to turn it back over to Kathy.
Thank you, Kelly. As Kelly said, the night of flight day 9, we'll close hatches, depress the vestibule, and prepare for undock the first thing on flight day 10. Flight day 10, the crew wakes up and immediately gets set to prepare for undocking. Undocking, as you'll see in the video, is off the V-bar, or the direction of velocity of the space station. And as we have done in the past, we will separate to approximately 450 feet. And at that time, the crew will initiate the fly-around maneuver. This video shows our fly around. It's sped up significantly. What you see here in just a few seconds actually takes closer to about an hour. We'll circle 360 degrees and then some around the International Space Station, and then when we get near the top, we will separate and target to be trailing the International Space Station by about 40 nautical miles. After separation, the crew again gets right to work performing robotic operations. This day we'll be doing the late inspection. The scans, which again you'll see in the video, are very much like the flight day 2 inspections. In fact, the procedure is the same, although we do eliminate some of the sensor calibration and the crew cabin survey portion. On flight day 2, the scans are primarily looking for damage caused by the launch environment. Here on flight day 10, what we're looking for are any micrometeoroid impacts that may have occurred while we were on orbit. And again, we're trying to ensure the integrity of the thermal protection system here before entry day. Flight day 11 is going to be our standard day before entry. We'll do a checkout of the orbiter's flight control system, and we'll do a hot fire of the reaction control system. Those are the jets that we use prior to when the aerosurfaces become effective lower in the atmosphere. And the bulk of this day really is spent on cabin stow, getting the vehicle that we've been using on orbit for almost 2 weeks now in a configuration to land. Flight day 12 will be our deorbit day. Landing will be just after 2 a.m. on March 26th at the Kennedy Space Center. Let's see, in summary, just this morning, I think y'all saw that Atlantis began its rollout to pad 39A at about 7:19 a.m. Central Time. This is a significant milestone, and it brings us one step, or I should probably say roll, closer to the launch of Atlantis. We are very excited, and we're looking forward to continuing the assembly of the International Space Station.
And Floyd?
Okay, thank you. Well, Kathy and Kelly have given you an excellent summary for this mission. And what I'd like to do next is give you another brief overview of the S3, S4 element and its subassemblies before taking questions. And we have a video we can roll. The S3 and S4 have been at the Kennedy Space Center since 2000 and 2001, respectively. The S3 arrived in December 2000 and the S4 in January of 2001. They were originally scheduled for flight in 2004, and the flight status was maintained for some time. Shortly after the Columbia accident, the flight status was rolled back, and we were able to replace a set of our batteries in this array, plus do some minor modifications to our external wireless instrumentation system. In the next slide, it's a picture of the S3 and S4. From right to left, the grapple fixture that will be used to remove it from the bay, the Sarge, the solar array blanket box, there's an upper and lower deck, and the on-orbit replacement units. Next slide. The primary portion or interface between the S3 and S4 is the solar alpha rotary joint, the Sarge. And some of the major components in this joint include 12 trundle bearings, 16 launch locks, 2 drive lock assemblies, 2 rotor joint motor controllers, 1 and 2, and a utility transfer assembly. Next slide. This is a view looking from the S3 toward the S4 inside the S3 truss. In the center top is the utility transfer assembly. Through this flows all the data and power back and forth between the rotating solar array wings and back to the station. And then there are 2 RJMCs which provide control of our drive lock assemblies to rotate the system. Next slide. This is a view of the Sarge from out looking in. On the right would be the S3 truss, and on the left would be the S4. So in the center here, we see 2 of the 16 launch locks for this system. Next slide. Another view of the Sarge, one of the 2 drive lock assemblies there in the center, and one of the 12 trundle bearing assemblies. There's a race ring gear. There's an outer and inboard of this gear in which the drive lock assembly interfaces. Next slide. Wanted to provide a view of the one of the solar array blanket boxes and the mass attached to that, and at the bottom of that mass is the beta gimbal assembly. And this is being one of the hoist activities while I was at KSC during assembly. Next slide. I have a animation that we'd like to run to demonstrate the rotation capabilities of this truss assembly. We start from the S3 to the Sarge, and then the S4. The upper and lower blanket boxes for the solar array wings. As in flight, the mass canisters will deploy out from the S4, and the blanket boxes deploy. And this demonstrates the 360-degree rotation capability of the Sarge, and also the beta gimbal rotation. In our next slide, we have a view of the solar array wings deployed, the current configuration of the ISS with the port side, and the remaining 2B wing that we will retract. And after this flight, we hope to see more symmetry with another pair of solar array wings on the starboard side. Next slide. I wanted to give a view of the photovoltaic radiator. This is a radiator used to reject heat from all the electronic systems in the equipment assembly in the S4. Next slide. And a deployed view of the PVR on flight. Once deployed, it will extend 44 feet, and it's 12 feet wide. Next slide. And this slide is a view of our keel, one of two keels that interface to the orbiter, cargo bay. The keel is the V-shaped assembly there at the end. As Kelly indicated earlier, during the mission, this will be removed and stowed internal to the S3 truss to allow the mobile transporter to transfer down to work site 1. And I have one more piece of video. Last week, we lifted the S3, S4 assembly into the canister. And once in the canister, we were able to roll this out to the pad earlier this week on early Monday morning. This is a view of the assembly being lowered into the canister. And once in the canister, as I said, we rolled out to the pad, and it sits there now awaiting the orbiter Atlantis for installation into the cargo bay. Thank you.
Okay, that concludes our opening remarks. So we'll open it up for questions here at the Johnson Space Center about the mission and its payload. We'll start around here. Go ahead.
Hi, it's Nancy Holland, KHIU. This may be just the simplest, dumbest question, but why does it work better when you let it sit in the sun for 30 minutes? What exactly is it doing to it? Is it the material itself that gets better? Why does it work better after it sits in the sun for 30 minutes?
Yeah, the panels actually, when they're cold, they tend to stick together. The coating that's developed on the panels will tend to stick together, and so as you warm them, it tends to release and lets the panels separate a little more naturally. So it's just the coating on the panels themselves tend to stick when it's cold and not stick when it's warm.
Adam Quinn with KTRK TV here in Houston. This is not a mission-specific question, but can you say how much or how little the Lisa Nowak situation has affected anything related to your training?
Let's see, I think I'll take that one. While we've all been aware of the news stories the past couple of weeks, the crew and the team in Mission Control have been focusing on the preparation of this mission. And so really from our standpoint, since our primary focus has been on the safe and successful execution of STS-117, we haven't seen any dramatic effects from the news stories.
Mark Carruth from the Houston Chronicle. I want to go back to the 116 mission and the difficulties that they encountered with the retraction of the ray. And it seems to me that that could be a particularly time-consuming activity that's sort of pivotal to future activities. And so bottom line, what I'm wondering is, what was the lesson learned from what happened on 116, and how have you changed, if you have, sort of fundamentally how you're going to retract this array? And I guess what I drew from your briefing was that you expect problems, but you're essentially going to do the same thing those guys did. And I just want to make sure I didn't misunderstand.
That's the basic plan. We do have a couple minor differences in hopes that it will help us prevent some of those problems. But again, we really probably won't know until we get there and try it. For example, to try to prevent the backward panel folding problem, what we're going to try to do first off is to reduce the tension on the blanket. We feel like maybe if we reduce the tension, that those hinges might lay properly and let the blankets fold up in the right direction. So we're going to try that, but like I said, our plan is built that if that doesn't work for us, then we'll have Pat and Steve out there, and they can take a tool and push on the hinge to get it to fold right, and then allow us to continue the retraction. So another difference that we're trying to do is this beta gimbal back and forth motion that you saw in a proactive manner. They did this technique on 12A.1, but it was after they'd already incurred problems. So we're going to try to use it proactively to prevent the guide wire hangups. But we're essentially doing a lot of what the 12A.1 mission did, because they went through the experience and had the lessons learned. So we're really just taking those lessons and incorporating them into our plan.
It's Mark Carreau from the Houston Chronicle. Again, to follow in the same vein, I heard you say, I think, you don't want to shake as much as those guys did. And can you sort of explain, you know, why? I mean, I know that was all new for them and they had to do what they could do, but
Right.
this time you made a point of saying you would like to avoid that. I want to make sure I understand why.
And you're talking about the spacewalking crew shaking the arrays? Yeah. Well, it was, I'd say, marginally effective during 12A.1. So it did take time. What they found during 12A.1 was that really the more effective technique was using the tool to move the panels past that part where it was getting hung up and redistributing the panels so that they were nice and even and horizontal, equivalent on both sides of the blanket. So really the lesson learned that we took out of that is shaking wasn't really an effective technique. It was more effective to redistribute the panels. We also took a look at it, and just from a lifetime loads perspective, we'd rather not put any more loads on the array than we have to, so that's why we decided not to shake the array.
Tracy.
Tracy Watson, USA Today. I'm not sure whether this is which person this is for, but since Lisa Nowak was the lead Capcom for this flight, I'm wondering what you had to do to readjust for her suddenly departing. Have you had to do more sims to include the new person, or you know, what kind of adjustments have you had to make?
I would characterize them as minor. The Capcom that has replaced her is Terry Virts. Terry was my Capcom during 115, and so he is familiar not only to me, but to the mission and its content, and also to the rest of the flight control team.
Kate Tobin with CNN. Back to the P6 array retract. Obviously, there was a lot of shaking. There was a lot of poking with tools that went on last time. When will you know if there was any damage done to the array during all of that handling and shaking that went on? And was there any thought given to, you know, maybe we're just putting, you know, good effort after bad. Maybe we should just take up a new array and not spend any more time trying to make this P6 array that's currently up there work.
Are you asking me about the array that was retracted on 12A.1?
Yeah.
Okay.
And the half that you'll be retracting this
yeah,
time.
Obviously there was a lot of discussion on what technique should be used to get that array in. Their objective was to get it retracted enough so that they could rotate that port side of the solar alpha rotary joint for power generation reasons. So it was a fairly methodical evaluation and a plan in terms of what they would go out and try. Now, of course, you can't retract. We don't have an array on the ground we can go practice on in the same environment. So it was a little bit of, okay, let's try this and see how that works. And if that doesn't work, we'll try something else. So the folks did go through a very thorough process of trying to figure out what options were available to them to try to get that array retracted, and then implemented them, saw how it worked, and adjusted their plan accordingly. As far as damage to the array, the crew did do an inspection prior to latching up the blanket boxes, so everything looked good before we latched up. We wouldn't expect any damage. The array will be redeployed at a later time, and then we'll see if there's any degradation of function, but nobody expects that. Again, it's really keeping eyes on it as we brought it in to make sure that it was going to come in and be retracted successfully. So same thing with this particular array, that we're going to keep our eyes on it and stop at any time if it doesn't look like it's working the way we expected it to. We do have, like I said, plans in place in terms of what we might go do if we see something a little unexpected. But if we see something totally different than the 4B, then we'll go through that same process where we'll talk about it, figure out if there's some other things that we ought to go do, and then put those plans in place.
Bill Harwood, CBS for Kelly. Two from me. Could you just walk me back through the retraction sequence, flight day by flight day, without everything else? Just on which flight day it's going to do what?
Sure.
I'm confused about the sequence. And your last answer, I thought that you guys did think you'd crack some coating or something on the retraction.
They do think there was some minor damage to the hinge and to a few cells, but Floyd could probably tell you how many cells, but what the minor damage that was done won't significantly impact the power generation of that array.
But that's part of the reasoning behind not wanting to shake these things, right?
Actually, that's part of the reasoning why we don't want to continue to retract if those panels aren't folding up properly. So we wouldn't want to try to overcome the force in that hinge and then potentially do cell damage. So that's why we're going to stop if we see the panels folding the wrong way and try to redeploy. And to answer your first question, to kind of summarize, because it is a very complicated plan, and the reason it's a little more complicated than you might expect is because our whole objective with this plan is try to reduce the overall time we spend on this array outside during the spacewalks. And we're trying to complete all the planned activities that we had originally had for this mission. So we're trying to minimize that time and trying to put ourselves in a good posture so that we can retract it remotely without the EVA crew's assistance. So we start out doing that because we think it's very likely that the panels are not going to fold up properly when we initiate the retract. We're going to start the morning of Flight Day 6, right before our second spacewalk. And so what we'll do is the ground will actually do some configuration. I talked earlier about how we're going to try to minimize the tension on that array to hopefully give us the best chance of getting the panels to fold right. So the ground will actually do that before the crew ever starts their activities. So it will basically be retracted about a half bay. So it won't be very perceptible, but we will have retracted it about a half bay to reduce the tension in that blanket. Then when the crew picks up that morning of Flight Day 6, they'll retract one additional mast bay. They'll evaluate, see if it looks like we have any indications of these panels folding backwards. If there are no indications, they'll do one more bay. If we do see indications that they're not folding properly, then they'll redeploy and try the retract again. And as I said, we really have a limited amount of time, so we may not have enough time to correct this problem by redeploying and reattempting the retract. On 12A.1, that's actually how they got past this particular problem, is they kept redeploying and re-retracting. But since we've only allocated about an hour, and it really depends on how the daylight passes line up on the timeline, but we're thinking max we'll probably have about an hour to deal with it that morning. So after our time is expired, then we'll press on with the EVA activities. And as I said, the first thing that the crew will do during that spacewalk is we'll put Pat on the arm. We'll have Steve Swanson also up near the blanket to help assist. And if necessary, we'll push on the hinge to correct that backward panel folding and retract. We're hoping that by the time we get to about 3 mast bays, we should have a good feel for whether the panels, whether we see nice crisp folds and that we've gotten past that problem. So that's really, at that point, once we see that we are in a good configuration to try to pick the retraction up the following day without assistance from the spacewalker crew, then we'll be done with that and the crew will move on to their other spacewalk tasks. So then we'll pick it up the following day on Flight Day 7. And right now we've got about 3.5 hours scheduled, but again, depending on the lighting requirements, the crew's just going to have to look out the window and see if they have sufficient lighting to watch and monitor the criteria that we have established. So we'll have a maximum of 3.5 hours to continue that retraction, and this is the part where we'll retract one bay, do that beta gimbal motion to go do the back and forth sinusoidal motion, see what we get, and we'll continue that until the point where if we have snags in these guide wires, till we have the blankets, we don't want to get them bunched up near the bottom of the blanket box. So if at any point we get a snag down close to the blanket box, that's when we'll stop and we'll finish it up the following day during the spacewalk. So like I said, depending on how successful we are on Flight Day 7, it's really hard for me to tell you how long we think we might be spending during that third spacewalk. But during the third spacewalk, our objective will be to retract it the rest of the way if we weren't able to get it all the way retracted. They'll also take a very good close look and make sure everything is in the right configuration before we latch up the blanket boxes. So that'll be the last thing that we do during that third spacewalk, is latch the blanket boxes with respect to the 2B array. Then they'll continue on if there's time available with the rest of their tasks.
Gina Sinceri, ABC News for Floyd. How challenging is it, everything that you're bringing up to the space station that's been sitting in storage for so long, to make sure that all of that is in working order? What do you have to do to rehab that before you launch when it's been sitting for a few years because of the Columbia accident?
Well, it's been sitting in a very controlled environment, and we've been able to recheck all the systems. And so we're very confident that this system is ready to fly again. As I mentioned earlier, It has been in storage relatively almost 6 years. We have changed out one set of our batteries, our lower deck batteries, for that reason. And we made some minor modification to a wireless instrumentation system. But we feel very confident that it's going to operate as designed.
Hi, Mark Kirkman with Interspace News. 2 questions, if I may. The first one is either for Kathy or Kelly. I'm a little ignorant on the process of how the array is retracted. Is it a fixed rate and it's simply a toggle switch or a software toggle? And is the starting and stopping, is that what puts unwanted loads in there? And for Floyd, I was wondering if you can characterize the material of the arrays to something that is that we'd be more familiar with, like maybe foil, or does it have a consistency of a hefty bag? In other words, what's the threat of potentially damaging, and what kind of texture is that array?
It's a very thin but tough laminar surface, almost like a plastic blind, as you've seen.
And your question about the retraction, I think you're asking me what mechanism do we use to get the array retracted?
Yeah, I'm just trying to understand. You have no control of the rate. It's simply it's on off. Is that really what it is?
There's actually obviously a motor that pulls the mast into the canister, and the mast members kind of fold up into that canister. So basically what you do is you command that motor on. It drives at a certain rate and brings the array in, and then the crew hits an abort command, and that stops the motion and powers off that motor. So that's how we control this one bay at a time, just by turning the motor on, commanding it to retract, and then sending the abort command to stop that motion.
In the back.
Hi, John Schwartz from the New York Times. With the new Sarge coming online, there were a couple of small glitches the last time around. You talked about lessons learned on arrays. What are the lessons learned on Sarge, and how are you prepared for that? And are there any issues of having both of them running at the same time now?
That's a good question. We did have, during the Port Sarge startup, we had learned something about how the software works to control that joint. The same software works for the starboard side joint, so we have made updates to our procedures to account for that lesson learned in the software. So we feel pretty good in that we've already checked out the port side, so we'd anticipate similar results with the starboard side in terms of the software functionality. Let's see, the second part of your question?
It was just whether having both running at the same time, is there any anticipated issue with that?
The only thing that we're watching is, depending on when we are under momentum management control with the CMGs, the control moment gyros, it is sensitive to disturbances. And so we are careful about when we start up those Sarges and when we stop them. And so there are some limitations on when we can start them both at the same time, or if we need to stagger them. So it adds one additional level to that piece of it. But basically, we understand the limitations, and we can work around it by scheduling how we start those joints up.
Hi, Lisa Baldwin, KPRC TV. I have 2 quick questions. Lisa Nowak's role as mission control communicator, could you elaborate for us what it would have been?
Well, Lisa was assigned as the CAPCOM, or capsule communicator, and that's the person who speaks basically for mission control to the crew during the mission. We have a team of 3 CAPCOMs, just like we have a team of 3 flight directors and flight control teams, and she was one of the members of the Orbit 1 flight control team.
And my second question, in light of her case, for this mission, will there be any more access to mental health services or any assessment that was not in place before?
I don't think that's a question appropriate for the lead flight directors here for the mission, but we can get an answer for that. We do need to go to other NASA centers to get questions now, and we'll start at NASA headquarters.
Copy. Thank you. This is Tarek Malik from Space.com and Space News. I think I have a question for Kathy. About the mission duration, you mentioned 11 plus 2 plus 2, and I was just curious, if you have, basically a glitch-free, spot-on flight, do you take advantage of those 2 days anyway? Mike Sapertini had mentioned you had a fourth EVA in your hip pocket should you want it. Would you use that just to perform some get-ahead tests?
Let's see, the plus 2 days that you're referring to really are for contingencies that are required for primary mission objectives, and if everything goes according to plan, we will execute the 11-day mission with 3 EVAs. That's the plan.
Great. Thank you very much.
Okay, and now we'll go to the Kennedy Space Center for their questions as well.
Todd Halverson of Florida Today, I think for Kelly Beck. Could you tell me what the upshot is if for one reason or another you are unable to retract the 2B array? Can you actually move the P6 array if 2B is only partially retracted? And if so, would you be able to get it out on the end of the port side of the central truss as you ultimately want to?
Well, all the analysis that has been done on the relocation of the P6 has been done assuming that the both arrays are retracted. I don't really think it's a matter of if we can get it retracted. It's really a matter of when. We have pretty good confidence that we'll be able to retract the array. We just don't know how long it's going to take. So, of course, if we got surprised and we had a problem, we'd have a lot of time before we plan on moving that P6 segment outboard. So we'd be able to take that time, take a look at our analysis to see if possibly we could relocate it with that array out. But I don't really anticipate that being the case. I think it's just going to take us some time to get it all the way retracted.
Just a quick follow. Can you tell me what your options are if that array, for one reason or another, does not retract?
Well, again, if it doesn't retract at all, now if we just need some more time, as Kathy talked about, we have a couple extra days on orbit that we could use to allow us to do a fourth spacewalk to go out and try to get that array retracted. If we don't get it retracted, we can still undock when we run out of mission time. We can take a look at and see what other options we have to us to get the array retracted. But again, I don't expect to get there. I think it's a matter of timing. So if we think it's the right thing to do, depending on what we see, we do expect to have some contingency days that we could use to get that array retracted. If not, we'll go do the proper assessments to figure out what our next step will be. Clearly, we'd like to get it retracted so that we can relocate P6 just as we plan to. So that would be the work that we would go off and do. And what we have taken a look at the various failure modes that could cause us problems retracting the array, and we have done some surveys of this array during the 12A.1 mission. During the fly around, they took imagery. LA took some photos during his spacewalk a few weeks ago and gave us some good imagery. We'll be taking some more photos from the space station. So we're able to go through that matrix of the potential failures that could occur and exonerate some of those based on what we can see with the array today. And again, we've not found any problems so far that would preclude us from getting the array fully retracted. Now, there's a couple things that we won't be able to detect. For example, a fray in the guide wire. The wires are so thin and the fray is really hard to detect. We don't have the resolution from cameras or even a set of binoculars to be able to see something like that. But as we bring that array in, and if we have problems, then the crew out during the spacewalk will have a close-up view of that, and then they can correct any problem with frays in the guide wires or such.
Okay, now we'll come back here to the Johnson Space Center for follow-ups. We have a few here.
Bill Harwood again. Just again on the following up on Tarek's question, I'm confused about contingency or mission extensions. If you launch early in the window, where you're not worried about flight day 4, which is my understanding, that's one of the reasons you kept it 11 plus 2 plus 2 is to protect for flight day 4 rendezvous. But if you get off early and do it flight day 3, do you not automatically extend this mission a day? Or are you going to, or what time? When do you have to when would you make that call? Is that if you see a problem with the array, then you extend the day, but otherwise you don't? I don't understand the sequence.
As Kathy said, if the mission goes nominally and we get all our planned tasks done, then we really have no reason to stay on orbit for a longer duration. But if we do run into problems and we think that we're going to need a fourth EVA or some additional time to get our mission objectives complete, then we'll talk about what configuration, what problems we've had, whether we could solve them with a fourth EVA. We'll have those discussions to determine whether we should extend the mission. But we do expect to have the consumables so that we could add a couple extra days. And adding 2 days versus 1 would give us the option of doing a fourth EVA without having them back to back. So in other words, we could have a day in between those EVAs to give us more time, put plans together, and think about our options.
But there's no need for just adding 1 day right away if you got off early for just to decouple late inspection from undocking or any of that stuff. You're just
No, we
don't
haven't.
need it.
As Kathy talked about, we've got late inspection on the undocked day, so we don't need an extra day with that from that respect.
Mark Carreau, Houston Chronicle. If I recall correctly, on the P3, P4 installation mission, there were some pretty sort of dramatic periods where there were some bolts that were stuck pretty tight, and especially if I recall correctly, they may have been on launch lock, potentially kind of showstopper bolts that would have prevented the movements of the arrays. And I wondered if there was anything about this payload that you changed or checked in light of that. I don't know if you can check tensions again or loosen stuff up if it's too tight, or operate different. I just wondered if that generated some sort of a change in procedure or payload.
Do you want to take the first?
Yes, it did. We went back and looked at all of our documentation regarding the installation of these fasteners on this S3, S4. What we found is that we saw some nominal running torques. Everything we expected was within normal limits. However, we were able to obtain a fastener that came back from the P3, P4, and as part of a material that we place on these fasteners that helps us maintain a locking feature, we think may have failed and contributed to some of our issues. One of the things we've done for this crew is provide a new tool, a torque multiplier that we'll use to give them additional capability. So it won't require a lot of work from the crew, as we saw in the previous flight, to release these launch restraint fasteners. That was the fasteners that gave them the biggest problems.
Go ahead, Mark.
Okay, so just to clarify, so I understand, basically what you did is go back through the paperwork and check the tensioning at sort of final assembly.
That's correct, the tensioning
and then give them something to put more muscle into this without them having to put so much physical muscle into it.
Correct.
Thank you.
And Tracy.
Tracy Watson, USA Today. Thanks. I think I have one for each of you. First of all, I'm wondering if when you retract P6, will the amount of power supplied by the new arrays just make up for the 2 arrays that have been retracted over the last few months, or will it be more? Will they add in more than that? And then a question for Kathy Kerner. Have you ever, in your experience, had a Capcom or another important member of the flight control team, like a flight director, have to be subbed in so close to a launch? Thank you.
No. I'll tell you that.
Let's see, the question about the power. We will actually wind up overall with more power generation capability, because we'll have the 1A and 3A arrays that not only are 2 additional arrays, but also, since they're able to rotate and track the sun with that alpha joint, we'll be in a much better power situation even after we retract the 2B array. Each array is about 14 kilowatts of power generation capability. So once we have 2 new arrays minus the old array, then we'll have about additional 14 than what we have today.
Kevin Quinn again with KTRK. We've been talking about the intricacies of this mission, but can you comment, please, generally on just how difficult all of this is and your general concern?
Were you addressing that question to?
I'm not sure.
Kathy, I guess.
You know, anytime we launch a space shuttle, it's difficult. And all of us who work in this business recognize the difficulties. And we train hard, we work hard, we coordinate and plan ahead of time to make what is very difficult seem very easy. But it isn't. It really is very complex. Anytime you're taking two very large vehicles and launching one into space to dock to the other one, again, it's highly complex and it's very difficult. But we spend a lot of resources planning for not only the nominal but the contingency type scenarios that we might run into, so that we can make the best use of the on-orbit time for assembling or for doing research.
And we'll have to wrap up our briefing now here with the mission overview. We'll take a break in our briefing schedule at the top of the hour to go to the Kennedy Space Center for a bit of commentary about the rollout of the Space Shuttle Atlantis, and then have our video file. And then our briefings resume at 11:30 Central Time with the spacewalk overview with lead spacewalk officer Keith Johnson, as mentioned. And again, the crew will be available for their briefing at 1 p.m. Central Time.